This video is about combustion analysis, and this is a um, kind of a complicated calculation that I think bothers a lot of people, but I think is inherently relatively simple. So let's go through the conceptual ideas behind combustion analysis. So we have a flask, and we want to perform combustion analysis. Remember that combustion is the reaction between a hydrocarbon and oxygen to form carbon dioxide and water. So we're going to put our unknown hydrocarbon into the flask, and we're going to add in some oxygen, and we're going to allow the reaction to proceed. So because the hydrocarbon is unknown, that's why there's an X and a Y subscript there. We don't know what those numbers are. And our goal in doing this combustion analysis is to figure out what those values of X and Y are so we can identify the unknown hydrocarbon. So we're going to find some product, right? Remember that combustion involves conversion of a hydrocarbon and oxygen into carbon dioxide and water. So we're going to analyze the products, and we're going to use the analysis to get information about what the unknown hydrocarbon was. So if you think about what's happening here, our products, the only carbon that's going in, since there's no carbon in the oxygen, the only source of carbon is the hydrocarbon. And the only product that contains carbon is carbon dioxide. And so we can look at the amount of carbon dioxide that's formed, and we can gain some insight into the amount of carbon that went in. So we're going to do this practice problem, combustion of 5 grams of an unknown compound that contains carbon, hydrogen, and oxygen yields the following products: 11.37 grams of carbon dioxide and 4.65 grams of water. What is the empirical formula of this compound? So we're going to do this practice problem next. So here we are combusting 5 grams of an unknown compound. We know it contains carbon, hydrogen, and oxygen. And we know our final products have the following masses: 11.37 grams of CO2, 4.65 grams of water. What is the empirical formula of this compound? So let's start with more of an understanding of what's going in here. So 5 grams of an unknown compound. We know the mass of the compound. We know it has carbon, hydrogen, and oxygen. The empirical formula will be CxHyOZ with whole number mole ratios. Let's start with carbon dioxide. 11.37 grams of CO2 form. All of the carbon that goes into this combustion reaction, all of it ends up as carbon dioxide. And the hydrocarbon, the compound, the unknown compound that we don't know what it is, that is the only source of carbon going in. And so we can use the quantity of CO2 that is produced, assuming that all 5 grams of the unknown hydrocarbon combust, and that there are no side reactions, and that there's no excess of that reactant at the end. You can assume that however much CO2 formed, all of that carbon that formed came from the carbon in the original compound. But remember, they're mole ratios that we need. It's not grams. And so we have to convert this 11.37 grams of carbon dioxide into moles of carbon eventually. So we start by converting to moles of CO2. Remember, you can't convert grams of a compound into moles of anything other than that compound. So we're going to start by converting the mass of carbon dioxide that forms into the moles of carbon dioxide that represents. But we need moles of carbon in the end. And so 1 mole of CO2 contains 1 mole of carbon. And so that means that this compound originally must have had 0.25, that looks like an 835 moles of carbon in it. So we're on our way, but now we need to move on to water. So the product water is the only compound on the right-hand side of the equation, the only product that contains hydrogen. And by the same description we had before, the hydrocarbon, the unknown compound, is the only source of hydrogen. So we can do the same thing by converting grams of water into moles of water, and then moles of water into moles of hydrogen, and that gives us 0.516 moles of hydrogen. Now, oxygen is a little bit more difficult. So if all this contained was carbon and hydrogen, we would be done. We would just need to see that we have twice as many moles of hydrogen as we have carbon, and we would say, oh, the molecular formula is CH2, or the empirical formula is CH2. But the problem is that it also has oxygen in it, and oxygen is a little bit more complicated because the hydrocarbon contains oxygen, but oxygen also goes in on the left-hand side of the equation as one of the combustion reactants. And both products contain oxygen, and so this is a little bit more complicated to figure out how much oxygen was there. So how many moles of oxygen? How do we figure that out? So if we go back, this is why it's complicated, is that the carbon, all the carbon comes from the hydrocarbon, and it all ends up as CO2. All of the hydrogen comes from the hydrocarbon, and it all ends up as water. But this Z, this oxygen that comes from the hydrocarbon, there's more oxygen that goes in because of the oxygen reactant, and it shows up in both products. So it's a little more complicated. So if we use all the information we're given, we know that we have 5 grams of our hydrocarbon. We can figure out what mass of that hydrocarbon comes from hydrogen and what mass comes from carbon, because we know the moles of carbon and the moles of hydrogen that are present. So all we have to do is convert the moles of carbon into mass, which we do here. So 0.25835 moles of carbon, if we multiply by 12.01 grams per mole, that's the atomic mass. That gives us 3.1 grams of carbon. So that means that 3.1 grams of carbon, 3.1 grams of carbon is present in this 5 grams total. And we can do the same thing for the hydrogen. And we converted 0.5162 moles of hydrogen into 0.5203 grams of hydrogen. We subtract that also from the 5 grams total. And then that gives us the mass of oxygen that's left over from this original 5 gram mass is 1.37687 grams of oxygen. And now all that's left is to convert that into moles. So 1.37687 grams of oxygen divided by 16 grams per mole gives us 0.086. So we have our moles of oxygen. These are the moles of carbon and moles of hydrogen from earlier in the problem. And then this is a mole ratio, but remember we need integers. So to convert these into integers, the easiest way to do that is to simply divide all 3 of them by the lowest number, which is 0.086. That's going to give us 1 mole of oxygen, and then some higher number values for the others. Moles of hydrogen is 5.9986, close to 6, and then moles of carbon is 3.002166. So these numbers are close enough to 3 and 6 to round them to 3 and 6. And so our final answer is going to be C3H6O.